Okay. So yesterday we start to discuss the CV characteristics of a MOS capacitor and MOS transistor. So going back to the MOS capacitor. So we started with MOS capacitor. So the difference between the MOS capacitor and MOS transistor is in the MOS capacitor we do not have the source drain regions, right? Other part is exactly same, right? So how to measure CV? So capacitance. So let me recap things little bit. So the capacitance is nothing but dq by dv, right? So if you're giving some voltage to the gate, right, how the charge in the semiconductor changes. So basically this is qs dqs by dvg, because your input is your gate voltage, and your charge qs is the charge in the silicon, right? So this is my gate voltage, right? And this is silicon charge, right? Charge in the silicon, right? So if I give a perturbation to the gate and how the charge in silicon changes, so that is my capacitance, and that capacitance is gate capacitance, right? Cg, right? Okay. So how do I measure, right? So basically you see your silicon charge is different in different region of operation, right? So we discussed about accumulation, depletion, and inversion. So in accumulations, we have positive charges accumulating at the surface. We have holes at the surface. Then if you go on increasing the gate voltage, then we enter depletion. So depletion, we have negatively charged acceptor ions. Then after some time, if still go on increasing the gate voltage, so we'll have depletion charge, as well as we have mobile electrons coming and and residing on the surface, right? So we have to scan, because when you want to have the CV characteristic, you want to scan all these regions. So that scanning is done using this DC gate voltage, right? So this VG here is the DC voltage, right? So this is the DC voltage. So DC voltage, you will vary all the way from, so basically it is given as a ramp, right? So it is give let me draw it properly. So it will be given as a ramp, right? So this is the VG that will give, this is the gate voltage VG. So all the way, so it will be your gate voltage, so less than flat band voltage, and in this case your gate voltage is more than threshold voltage, right? So you are scanning your DC gate voltage below flat band voltage all the way above inversion, right? Above threshold voltage. That means you are going from accumulation to inversion, right? And let's say I'll put couple of points. So let's say this is one, right? So this is where the gate voltage is VG equal to VFB, right? Your gate voltage equal to flat band voltage, right? So okay, let me do it differently. Okay, so let's say this one is your VG equal to VFB, right? So this is point 2, let's say, and point 1 will be somewhere VG less than VFB. So your VG less than VFB. So let's say this is point 1, right? And you will have in between, you will have somewhere VG equal to 0, right? Gate voltage equal to 0, right? So let's say this is point 3. Then at point 4, your VG equal to VTH, right? And point 5 is, this is, let's say this is point 5, and VG greater than VTH, right? So these are 5 points. So now scanning the gate voltage, when increasing and giving a ramp, right? Your gate voltage is increasing, right? So I'm scanning these 5 different points, right? Now at every point, right? So I'll give a AC signal, right? So basically, I'll fix my VG at this point. Then I'll give on top of that, I'll give a small signal. Basically, I'll give a perturbation. So this perturbation is nothing but my delta VG, right? So I'll go to each and every point. Let's say I'll go to point 1 and perturb the gate voltage, right? and find how the charge changes, right? And that charge, so if I give a perturbation here, delta Vg, so there will also be a perturbation in the charge, right? So basically, let's say, um, okay, so let's say I am operating at point 1, right? Point 1. So your Vg is less than flat band voltage, right? Vg is less than flat band voltage, and you have some charge in the silicon, right? At this gate voltage, right? And this charge in the silicon is nothing but your accumulation charge, right? Your accumulation charge, and that is accumulation charge is nothing but in case of NMOS transistor or in case of this capacitor. So this is holes accumulating at the surface, right? Now, if I give a perturbation, that means I have a DC voltage, and I'll give this perturbation delta Vg, and this delta Vg is a AC, right? And with a fixed frequency, let's say this is at 1 kilohertz, right? I'm giving a perturbation that is a AC signal which is varying at 1 kilohertz. The frequency of the AC signal is 1 kilohertz, right? So if I do that, then I'll have silicon charge that will also perturb, because your Vg is perturbing. So your silicon charge will also perturb, right? Right. And my capacitance, right? The capacitance that I'm talking about, gate capacitance, is nothing but in this case will be this one, right? Del Q by del V, right? Del V. Okay, so this is how you measure. So generally in the lab, this is done by a CV meter. So we have a capacitance voltage meter, which gives a ramp, DC ramp, because ramp, and at every point it also perturbs, right? So it could give steps, right? So at every step it also perturbs and measures the small signal current, and small signal current is converted to charge, right? From there they find the so means the meter, the CV meter finds capacitance, right? Okay, so if this part is clear, so let's go to our first thing. Um, right. Uh, so let's say your Vg, in this case, your gate voltage is less than flat band voltage. So this is the case point 1, right? So the case 1, right? Okay, so here my silicon charge is nothing but your accumulation charge, right? And that part we know, the accumulation charge I could write down is Q psi s by 2 kT. So here in this condition, your psi s is negative, right? So your accumulation charge will be K1 means some constant times e to minus Q psi s by 2 kT, that we have derived, right? Right. So if you want to find CG, right? So if I pot of it, right? So when I pot of, right? So basically I'm changing the QSI, right? So if you see, means I'll draw. So so if I'm giving a delta Vg here, so let's say I'm giving a voltage delta Vg. This is the perturbation voltage. So this delta Vg will have some part, some voltage delta psi s, right? Right. Okay. So here this, you know that delta, see your Vox, we know that your Vox is nothing but your silicon charge by Cox, right? And you know that Q silicon is nothing but Vox times Cox, right? Because this is in the accumulation. So you know this, right? So Q silicon is nothing but Vox times Cox, which is nothing but Q accumulation in this case, right? So if I do similarly, your delta Vox also will be Q accumulation, right? Delta Q accumulation divided by Cox, right? Right. So if I do delta Vox by delta Q accumulation, so this will be nothing but 1 by Cox, right? Okay. And okay, so this is this part, um, right? So if I'm doing delta Vg equal to delta Vox plus delta psi s, so if I divide everything by delta Q silicon, So this is delta Vx by delta Q silicon plus delta psi s by delta Q silicon, right? And this is my gate capacitance 1 by Cg, 1 by gate capacitance, and this is 1 by Cox. And this capacitance is nothing but your uh, semiconductor capacitance, right? So semiconductor capacitance Cs is nothing but delta Q charge in silicon. How the charge in the silicon depends on delta psi s. Delta psi s is nothing but the drop in the silicon, right? So psi s surface potential is nothing but the voltage drop in the silicon, right? So charge in the silicon by voltage in the silicon, this is your Cs, right? Okay. So now if I want to find Cs, right? So this is nothing but dq silicon by d psi s, right? So in the small singleton I could write it, right? And in this case, in case one, so this is nothing but the accumulation charge, right? Accumulation charge. So and accumulation charge I told you, so this will be some constant times e to the power minus q psi s by 2 kt, right? And so I could still write it as e to the minus q psi s by 2 kt if I take the differentiation by q by 2 kt into, right, minus. So this is your charge, this is your silicon charge. So this part, if you look at this part, this is your silicon charge. And silicon charge means basically this is your accumulation charge at that point, divided by into minus q by 2 kt. So if you see, this is 2 kt by q, right? So this is your Cs, right? So you see, if you look at this Cs, right? If you look at this semiconductor capacitance in accumulation, right? So your capacitor is in accumulation, and the Cs is the silicon capacitance, semiconductor capacitance in accumulation. So this is Q accumulation divided by 2 kt by Q. And 2 kt by Q at room temperature, if you see, this will be around 50 millivolt or 52 millivolt, right? Let's say if you do, right, 52 millivolt. And Q accumulation is a good enough number, right? This, right? So this is a very high. So what my point is, this Q accumulation by 52 millivolt is a very high number, right? It's a very high number, right? So now if I write 1 by Cg equal to 1 by Cx plus 1 by Cs, so Cs is very high, right? Cs is very high generally, and Cs is very high, or Cs you could write Cs is much higher than Cox, right? So your 1 by Cg, you could simply write as 1 by Cox, right? And your gate capacitance is nothing but your Cox, right? So in the accumulation, so now when you're operating your capacitor in accumulation, or your transistor in accumulation, your gate capacitance is nothing but it will be Cox, right? Your oxide capacitance. Okay, so this is from the mathematics, right? So this is, we have derived and we found out, okay, Cg equal to C oxide. So what actually happens? Uh, uh, what actually happens in reality, right? If you see, right? So when I'm perturbing, right? So let's say, um, so I have my capacitor here, right? And this is my gate, right? This is my gate, and this is the ground. So I have already given, let's say, Vg less than Vfb. So I have a sheet of holes at the surface. I have a holes at the surface, right? So now, if I perturb it, right? So if I give delta Vg, if I give delta Vg here, so I am getting delta psi s here, right? So you know that your charge, when accumulation, your charge or accumulation charge depends exponentially. So excuse me, just a minute, I'll just come back. Okay, so so your accumulation charge will change exponentially with delta psi s, right? So little bit change in delta psi s, your accumulation charge will change by a large amount, right? So we have seen, right? So if you see, we had earlier seen, right? So if you plot your psi s, psi s and qsi, right? So in the accumulation region, right? Accumulation is exponential, right? So it's exponential, right? This is accumulation, right? Right? And this is e to the power minus q psi s by kt to kt proportional to, right? So little bit change. So if you see little bit change in delta psi s, right? So let's say if you're changing delta psi s by little amount, right? So your accumulation charges, since it's exponential dependence, your accumulation charge is changing very high, right? So that's the reason your silicon capacitance at CS or CS, right? So this is quite high number, right? So that's the reason you have to neglect 1 by CS, and your gate capacitance will only be 1 by COX, right? And also you could think of in another way, right? So when you're giving delta Vg, right? When you're giving some delta Vg, so you're changing also the electric field, right? Right? But the electric field could not penetrate because you have accumulation layer which is sitting at the surface, and this concentration of this charge is very high. So your electric field cannot penetrate. So basically, whatever extra charge you give to the gate, delta Vg is, that is nothing but you are giving extra charge to gate, and that extra charge will come to the accumulation, right? And since this is like a parallel plate capacitor, right? So because your accumulation charge is just sitting below oxide and your gate charge is just above oxide, so the capacitance that will have is C oxide. And so you could think it in a different way, but mathematically, in accumulation, your CG, the gate capacitance will be C oxide, your oxide capacitance. Okay, any questions here? So if not, so then let's go to a point where your Vg is greater than VFB. So Vg will somewhere between VFB and your VTH, right? So if your Vg is somewhere between VFB and VTH, that means your transistor is in depletion, your capacitor is in depletion, right? So depletion, what do you mean by depletion here? Depletion means we have positively charged acceptance here, right? And negatively charged acceptance here, right? We have negatively uh, charged acceptance, and your Q silicon, in this case, your Q silicon is nothing but your depletion charge, right? So we are assuming means your inversion, there will be some inversion charge, there will be some electron, but that electron concentration is much lower than the inversion charge, is much lower than the depletion charge, right? So this is nothing but QD, and QD is nothing but QNA times WD in this case. And we know, right, this is 2 epsilon Si QNA root over psi s, and I told it, okay, this is some constant root over psi s, right? So your charge, I mean, in this case, your QSI is nothing but K2 times root over psi s, right? So again, so if I write my semiconductor capacitance, because if I look at my semiconductor capacitance, so this is nothing but dqsi by d psi s, right? Right, and if I do the derivative, d by d psi s, k2 root over psi s, so this is nothing but k2 by 2 1 by root over psi s, right? And so basically, this K2 means basically if I expand it, right? 2 epsilon Si QNA 1 by root over psi s. So if you do that math, so this will be epsilon si by wd, and your wd is, you know, right? Your wd is, your depletion width is nothing but epsilon si psi s by q, right? I'll not do this math, right? You could figure it out, right? So you see, in the depletion, right? So when your Vg is somewhere in the between flat band voltage and Vth, right? So your capacitor is in depletion, or your transistor case also it will be in depletion. So your CS, right? Your CS, your semiconductor capacitance will be epsilon Si by Wd, right? So what is happening, right? If I'm perturbing here, right? So basically, let's say I bias somewhere between VFB and VTH, and I'm perturbing the gate. If I'm perturbing the gate, my WD is changing, right? My depletion width is changing, right? And this capacitance is simply the depletion capacitance, right? And this capacitance, if you derive, this will be epsilon Si by WD, right? And um, and you see, if you see, your 1 by Cg is 1 by Cox plus 1 by Cs, right? So uh, so this will be 1 by Cox is nothing but, or I could write down 1 by epsilon Sci by Tox, and this will be 1 by epsilon Si by Wd, right? So this is Tox by epsilon ox plus Wd by epsilon, right? This is 1 by Cg, and you know that epsilon Si is almost 3 times of epsilon ox, right? Because this is 11.9 for silicon and this is 3.9 for oxide, right? This is almost 3 times. So you could also write down this as 3 Tox by epsilon ox plus Wd by 3 epsilon ox, right? So 1 by epsilon ox if you take, so this will be right. So your Cg, your gate capacitance in this case is 3 epsilon ox, right? 3 ox plus Wd. Right. So this is just one mathematical form of looking at this gate capacitance, right? So what is happening, right? So see, basically your gate capacitance in this case, because if you look at, right, your epsilon ox is constant, your Tox is constant because your oxide thickness is constant in a particular technology. Only thing what is changing with gate voltage, right? So if you bias, if you change the gate, because this is a big range, flat band voltage all the way to VTH, right? That means if you bias somewhere, that means your WD is also changing, right? So your gate capacitance will depend on WD, right? So your gate capacitance is proportional to 1 by WD, means if you increase WD, your gate capacitance will reduce, um, right? And and WD, right? So your WD will increase with VG, right? So WD is proportional to gate voltage. So your CG is proportional to 1 by gate voltage, right? So so here, if you look at the accumulation, right? Your CG is Cox, right? Accumulation, once the transistor enters accumulation, your capacitance is fixed at Cox, right? Right. But between when your transistor is in depletion, your capacitor is in depletion, that is somewhere between VFB and VTH, right? So that means your gate capacitance is inversely proportional to 1 by Vg, right? Your gate capacitance is inversely proportional to 1 by Vg. So as you go on increasing your Vg, your capacitor will reduce, right? Right. So this is a important part, right? So we'll come back to this a little bit later. Okay, so if this is done, then I'll go to the next thing. Please interrupt me if you have any question, right? Um, I'm assuming that I'm clear, and I think you are following. You could follow me, right? So let's say this case, your Vg is greater than threshold voltage. This is very interesting, right? Because your VG, so your VG is greater than VTS. That means your Q silicon, right, has inversion charge plus depletion charge, right? And we have already discussed, right? So your QD, so what will be your Q inversion? But your QD will be root over 2 epsilon Si QNA, right? Because your we discussed your surface potential will be fixed at 2 psi b, right? There will be very less change, right? And your it could, this will also be some constant into Q to the power psi s by 2 kt, right? Right. Okay. Let's see. Let's not put 2 psi b here. Let's say this is psi s, right? And I could have some constant here k1, k2, root over psi s, right? Okay. So your Q silicon in this case has two components. One is inversion charge, other one is depletion charge, right? But depletion charge, so if I see how your Q silicon, if I give a perturbation now, your psi s is changing, right? So how much the silicon charge changes, right? So so basically you see, uh, again you could think of, right? So once the transistor, once the capacitor enters inversion, right? So we discussed, right? Your depletion charge is almost fixed, right? So there is a small change, because if you see, we have plotted this Vg versus psi s, right? So we saw that your psi s is almost fixed at 2 psi b, right? 2 psi b after inversion. So there is a very small change, right? Very small change, but there is a change that, so and we assume that this is fixed, right? Right? But there is a very small change. So you could see from here your depletion charge is almost constant, right? Because if you have seen, if you see psi s as a function of Q silicon. So we had seen that, right? So we have your depletion charge, which is root over psi s, and we have our inversion charge, which is exponential psi s. So if you add both of these, so basically you have some charge, something like this, right? So this is your Q silicon, right? So this is your uh, depletion charge, this is your inversion charge, but and this is your Q silicon, right? Right. So, and we are operating somewhere here in this case, in the condition, we are operating somewhere here, right? Your this is your this part is your 2 psi b. So this is 2 psi b, and we are operating somewhere here, right? So somewhere here we are operating, right? We are, sorry, right? So we are operating somewhere here, right? We are operating somewhere here, right? Okay. So here if you see, your inversion charge is much higher than your depletion charge, right? And even if psi s is changing little bit, your QD is changing very slowly, right? So we could neglect, so if you look, you're from the Q silicon, so we could neglect, so we could write your Q silicon is mostly equal to approximately k1 e to the power q psi s by 2 kt. This is in the inversion. So if I now do uh, derivative of this will again be q silicon, or this is q inversion, right? Uh, Times q by 2k t. So this is nothing but again q inversion divided by 2kt by q, right? And this is also a big number, large number, right? So this also a large number, right? So in the denominator we have a 2 kt by q, only 52 millivolt, but q inversion is very high, right? So if you are biasing your capacitor or transistor in the inversion, you have lot of electrons, your inversion charge is much very high, and but in denominator you have 52 millivolts sitting, right? So So this 1 by CS, the CS, right? This CS, right? Not 1 by CS. This CS is pretty high number, right? In inversion also, right? So now if I do means if I write down 1 by CG equal to 1 by Cox plus 1 by CS, so here the CS is very high, so this will again be 1 by Cox, right? So in the inversion, inversion, your CG will be Cox, right? Your gate capacitance will again be oxide capacitance, right? So you could also imagine this way, because the moment you have inversion, so you have a seat charge sitting here, and this seat charge is your electrons, right? So you have a seat of electrons sitting here, sitting there, right? And if you pot up their VG little bit, right, your inversion charge will pot up, right? Because your depletion charge is not changing much, right? Your inversion charge will pot up. That means, so you could think of it as a parallel plate capacitor, right? So one plate is your seat of electrons, other plate is your gate, right? And you have oxide thickness in between, right? So your capacitance will be simple Cox, right? So in accumulation, your capacitance is Cox. In inversion, your capacitance is Cox, right? And there is a change in between, right? So now if I plot, right? So let's say, let me plot, right? So this is my gate capacitance, and this is my VG, right? And let's say this point is okay. So yeah, so your flat band voltage is negative anyway. So let's say this is your flat band voltage, VG equal to VFB, right? And this is your voltage, VG equal to VTH, right? Roughly, right? Let me. It's not to the scale. VG equal to,
Graph is like parabolic, right? In this case.
okay. Some questions. Okay. So VG equal to VTH, and this is Cox here. Let's say this capacitance Cox, right? So okay. So this part is accumulation. So your capacitance is Cox, right? Right? And this part is inversion. Your capacitance is Cox, right? But in between, right? So in this region here, so if I see in this region, your transistor is in depletion. It means your capacitor or transistor is in depletion, right? So so your capacitance means as the VG is increasing, your depletion width is increasing, so your capacitance is reducing. So your capacitance will slowly reduce till this point, right? So this is in the depletion, right? Your capacitance is reducing, and right. So right. Then after VG equal to VT, you have a lot of inversion charge, so the capacitance will suddenly increase again, right? So this is your CV characteristics, uh, right? So in the accumulation, your capacitance is Cox, and in inversion, your capacitance is Cox, and in between there is a change, right? And that is your um, uh, means there the capacitance will reduce with increase in VG. This is because your depletion width is increasing, right? And then the moment your transfer capacitor inverts, your will shoot up, right? So this is um, Yeah. So this is the CV characteristics. So this is your CV. Your CV characteristics, right? Right. So please, I mean, any questions here? Any questions before I go to the next step?
So can you please explain again, like why an accumulation and inversion? Like I understood mathematically, but physics-wise, why is it happening that accumulation or inversion may it is coming as COX?
See, in accumulation and inversion, both the cases, you have in the accumulation case, we have lot of electrons sitting at the surface, and in inversion case, we have lot of in accumulation case, we have lot of holes sitting at the surface. In inversion case, we have lot of electrons sitting at the surface, right? This part clear, Monica?
Yes, sir.
So if a perturbing gate, right? So this electron hole concentration is also perturbing, right?
Yes,
Right.
sir.
So what I was telling is, right. So you could think of this as a parallel plate capacitor, right? I have my oxide, silicon dioxide, and on top I have my gate. So this is my gate, let's say, right? This is my gate, right? And in the bottom I have in the accumulation case I have holes sitting here, or in inversion case I have electrons sitting here, right? Right.
Yes,
So this is something you could imagine it is like a parallel plate capacitor, right? Right.
yes, sir.
And electric field is not penetrating. Electric field could not penetrate because we have lot of holes, lot of charges sitting at the surface, right? Electric field could not penetrate, right? Right. So if electric field is not penetrating, that means in inversion case, when we have lot of electrons, so if I do the inversion case, I have lot of electrons at the surface here, and also I have acceptor ions, right? Right. But this perturbed electric field, see, basically you could think of when you're changing VG, your electric field is also changing, right? But this electric field is not penetrating your electron layer, right? And so there is no change in the depletion charge, right? So whatever changing is changing, only electron concentration is changing, right? So that's the reason you could think of it as a parallel plate capacitor, and your parallel plate capacitor means your capacitance will be only Cox, right?
Yes, sir.
Okay.
And so the direction of electric field.
Yeah, see, okay. So if your VG is positive, let's say in inversion, right? Let's say your VG is more than VT, inversion case. So your direction of the electric field is this direction, but the magnitude of this electric field is increasing or decreasing, right? Because if you are perturbing VG, your electric field magnitude also increase or decrease, right? But
Yes,
it is
sir.
still positive, right? It will still be positive.
Okay.
But
Okay,
in
sir.
accumulation case, your electric field is opposite direction, so
Yes.
it is negative. That magnitude will increase or decrease, but that field will be positive. Sorry, negative, right?
Okay. Yes, sir. Understood.
See, you could see because see again, right? So since there is exponential nature, right? Your accumulation charge or inversion charge, they vary exponentially with psi s, right? So actually, since it vary exponentially with psi s, so your semiconductor capacitance is very high, right? If somebody is varying exponential, little bit perturbation, your charge will increase exponential. That means your capacitance is very high, right? Right? And that's the reason 1 by Cs you have to neglect, right? All right.
Yes, sir.
So
Understood.
yeah, any other questions?
Yes, sir. So likewise for depletion region, we can say that our distance between the parallel plates is increasing because of depletion.
No, it's
So
not.
that's why.
Yeah, you could think that. Oh, yeah, this is like a depletion region there, right? WD. Huh?
Huh. So since in depletion region, we assume that depletion approximation applies. So there are no charges. So ultimately, the distance between the capacitance plates are increasing.
Yeah,
So hence capacitance
the
remains.
yeah, you could see that yeah, width of the insulating region is increasing.
Hmm.
Right? Yeah.
Yes, sir.
So this is same as parallel plate. The distance between two plates are increasing, right? Because
Yes.
WT is changing, right? Huh.
Huh. Yes, sir.
Okay. So again, right? So what I told you, right? Your Potter basin frequency is 1 kilohertz, right? And in a MOS capacitor, how is inversion layer formed in MOS capacitor? Because MOS capacitor do not have this n plus layers, right? Source and layers, right? So basically, these electrons are formed because of your thermal generation, right? Because your field becomes so high that your thermal generation happens. So electrons from valence band goes to the conduction band and form the inversion layer, right? But again, right? So because when I'm talking about the frequency, so basically when you are giving a perturbation which is varying very fast, right? So this thermal generation is a very slow process, right? And we have, I mean, I think you could find it in the book. The thermal generation takes few microseconds, like few microseconds. Thermal generation is a very slow process, right? So if you are giving a very high frequency, right? So let's say you are perturbing your gate voltage at a very high frequency, right? So right. So then your inversion layer could not be generated. Inversion layer could not respond, right? So basically, even if what I'm telling, um, right? So I'm let's say your capacitor is in inversion, right? So you have your gate oxide, your silicon dioxide, and you have electron concentrated electron here, right? A seat of electrons, right. But now if I'm perturbing, I have some Vg, but let's say I'm perturbing this with a 1 megahertz perturbation voltage, right? So this delta Vg is varying at 1 megahertz, right? So as you go on increasing this frequency, right? So when you're perturbing Vg, that means when you're perturbing Vg, you are changing the Vg, your inversion charge is also changing. That's the reason your capacitance is Cox, right? Right? It is responding, right? Your inversion charge is responding to that perturbation, right? But once you increase the frequency, your inversion charge will not respond, right? Because again, this is minority carriers and this is generated to thermal generation, and the response time is in the order of microseconds. So if you're changing your voltage very fast, right? In 1 megahertz means you are changing very fast, right? In microsecond order, right? So your inversion layer could not respond, right? So that's why when you go to very high frequency, right? When you do the CV measurement at a very high frequency, right? So there you will see that in the moment it reaches inversion, your capacitance will not change. Capacitance it will not go to Cox. This is because your inversion charges are not responding, right? This is for the high frequency case, right? High frequency case, right? High frequency means if it is more than hundreds of kilohertz, right? If your voltage varying time in the order of microsecond, so your minority carriers cannot respond, right? Your electrons, your inversion charge cannot respond, right? So if the inversion charge cannot respond, that means I'm giving delta Vg, my delta Q inversion is 0, right? That means your capacitance will be very less, right? Right. So this is a typical phenomena that we observe in MOS capacitors because of high frequency. Because when you measure the CV characteristic at higher frequencies, right? But in case of MOS transistor, we do not generate those electrons thermally, right? We have N plus region sitting here in MOS transistor. In MOS transistor, I have N plus regions here, right? I have N plus regions, right? And if I'm perturbing this Vg, right, my carriers, I have let's say I'm biased in such a way that I have some electrons already here, right? Now if I give this perturbation of delta Vg, right? So when the perturb this delta Vg, the electrons are not thermally generated. Please keep it in mind, in MOS transistor, the electrons, the inversion layer electrons are not thermally generated. They are injected from source and drain area, right? Because I have a lot of electrons sitting in source and drain. This is N plus region, right? But there is a barrier, right? The moment you pot up delta Vg, so your barrier is pot up. So this is the injection, right? And injection can be means it can happen very fast, right? Thermally generation takes time, but injection over the barrier can happen very fast, right? So that's the reason in MOS transistor, your low frequency CV characteristic and high frequency CV characteristic at any frequency if you measure in the MOS transistor, it will be same, right? So you will not observe this CV difference with frequency in the MOS transistors. You will only observe it in the MOS capacitor, right? That's the reason in the books also you'll see that you have a low frequency CV and high frequency CV characteristic of a MOS capacitor, but not for a MOS transistor. Because MOS transistors, your electrons are generated uh, by injection over the barrier. They are coming from source and drain area. So you do not, means that is not limited by the frequency, right? So you could, MOS transistor could respond very fast. So yeah, so if you MOS transistor, if you go to the lab and do a CV characteristic of MOS transistor, at any frequency it will give you the same characteristic, but MOS capacitor will not. All right, any questions here?
Sir, in MOS capacitor, if our capacitor is already biased in inversion region, there will then even after perturbing, there will always be an inversion layer there.
Yeah, but I'm not. I am talking about delta Q inversion, right? Not Q inversion. So if I'm giving a perturbation, how is Q inversion changing? So Q inversion changing means you have to have more thermal generation, right?
Yes, sir.
So if Q inversion is constant, that means my delta Q by delta V will be 0, right?
Yes, sir.
Right? Please, capacitance is delta Q by delta V, not Q by V, right?
Yes, sir.
So you will not have this delta Q in case of MOS capacitor if you are perturbing at high frequency, right?
Yes, sir.
Okay. Anything else? Any other questions? I am Swati, Aditya.
No, sir.
All right. Okay, so then we have done the CV part. Before
Sir, I have another question.
Yeah, please.
Sir, how will our CV characteristics change if our oxide layer also has charges?
Oxide layer?
Our oxide also has charges in them.
Oh yeah, that's a very good question. Very good question, right? So yeah, so I'll just take it. So what will change with oxide layer is not the COX, right? So what will change your threshold voltage, right? So you will have a shift in CV characteristic, right? So let me remove this high frequency case, right? So what will happen that when you have negative charges in the oxide, that means your VT is increasing, your threshold voltage is increasing, right? So your CB characteristic will just shift, right? So they will shift, right? Because your VT point has changed from this point. Let's say it has changed to this point. So right. So basically your CV will just shift, right? So they will shift. Right. So basically it will just shift, right? Because your threshold voltage is changing, but your COX, your depletion charge or depletion region width is not changing, right? So you will see a shift in the characteristics. So your threshold voltage changes, you will see a shift in the characteristics, right? Okay, so if this threshold voltage change is because of charges, your oxide charges, right? So let's say your threshold voltage could also change by changing the oxide thickness, right? If you increase the oxide thickness, your threshold voltage will change, but your Cox will also reduce, because Cox will also reduce, right? So you see, so your Cox will also reduce, all right? And so there will be a change in threshold voltage. There is a change in oxide thickness. So oxide thickness, oxide capacitance. So you could plot it, right? Right. So if your threshold voltage, changes uh, because of oxide, if you change the oxide thickness, right, your threshold voltage will move, right? Your threshold voltage will move, but your capacitance will also change, right? So your capacitance will change. So right, so your capacitance will also change, right? So you'll have your Cox will also change here, right? Your this is earlier Cox, then this is new Cox. Your VTH will also change, right? So this is if your threshold voltage changes by change in Cox, right? Right. Basically, VTH increases by increasing the oxide thickness, right? So, but your capacitance is also reduces. Cox also reduces. So you'll see this kind of things, right? Um, right. But let's say your threshold voltage changes by changing the what, by changing Na, right? So okay, now your threshold voltage changes. Let's say you have two cases. One case, I have a doping of 10 to the 17, the substrate doping, P sub is 10 to the 17, P sub 1. And other case, I have P sub 2 is 10 to 18. How the CV characteristics change? How will the CV characteristics change? Anybody? Om?
Sir, my threshold voltage would increase.
Threshold voltage will increase. Threshold voltage will decrease.
Increase.
Yeah, threshold voltage will increase. So will there be a parallel shift in the characteristic, or your Cox will not change? Your threshold voltage will change. Will there be any other changes? Hmm? Anybody else? Sarda, Monica? No?
Sir, my depletion.
Yeah, so your depletion width will also change, right? So in the depletion region, it will also be different, right? Okay, so I'll give you as a homework, right? So you think about it, right? So what will happen when I'm changing the substrate doping? Your threshold voltage is changing, your oxide capacitance is still the same, but your depletion region WD, right? Your WD will modulate differently, right? Because your doping has been changed, right? So your WD, so this part, so this part here, right? This part here will also change, right? This part, right? And how this change, please figure it out, right? I'm not going to tell it here, right? So because you means because this is so this part, right? From going from accumulation to inversion, this is mostly because of the change in the depletion width, right? And your depletion width will change differently because of your different doping, right? So figure it out. Okay. Any questions? Yeah, why all of you are silent? Speak up, right? So, all right. So, before I go to the current voltage characteristic of the MOS transistor, uh, I'll just tell you one thing. So, yesterday we talked about your NMOS transistor, right? In NMOS transistor. So, in NMOS transistor, so your metal, your gate is made of N plus polysilicon, right? So when I talk about N plus polysilicon, this is highly doped, right? So this is highly doped, right? So highly doped in the sense it is around 10 to 20 to 10 to 21 per centimeter cube, right? So because of this, because we have a N plus polysilicon sitting there, so let me draw, right? If this is my substrate, so this is gate, source, anyway source and then I grounded. Right? This is my N plus polysilicon, right? So here, um, see, we assume that polysilicon is very highly doped and it will behave as metal, right? But even because even if it is very highly doped, it cannot behave like a metal. So what happens, right? So when you're applying very high gate voltage, right, your VG is much higher than VTS. Let's say you are applying very high gate voltage, right? So we have an electric field in this direction, right? But if you look at this interface here, right? If you look at this interface here, um, this interface here, right? So we never talked about that interface, right? Because we talked about silicon dioxide interface, right? Silicon dioxide interface, but we never talked about polysilicon and silicon dioxide interface, right? Even if this is highly doped, so because this is N plus polysilicon, so we have lot of electrons there, right? Right, and electric field at this junction, electric field at polysilicon and silicon dioxide junction will also be very high, right? Um, so because of this high electric field, so the electrons will deplete from the surface of polysilicon when you go to very high gate voltage, because the your gate field is increasing, right? Your gate field is increasing. So the electrons will deplete, right? So what will happen? The electrons at the surface, will deplete, right? Because of the very high electric field, the electrons will be repelled from the surface, right? So what will happen? There will be a region which will be depleted, right? There will be some depletion, right? And that depletion will only happen at very high gate voltage, right? So let's say for a typical transistor, if your threshold voltage is around 0.4 volt, but you are applying 1 volt gate voltage, right? That means you are applying very high electric field, right? Right. So in that condition, so your polysilicon will also be depleted, right? Because very high electric field and electrons will be repelled from the surface. So your polysilicon will be depleted, and that phenomena we called the polysilicon depletion, right? Polydepletion effect, right? Right. So because of the depletion, so there will be a region which is not very highly doped, right? So we talked about VG, when you're applying some gate voltage, we talked about VG equal to flat band voltage plus oxide, um, uh, drop across oxide plus is drop across silicon, right? But then because of the polysilicon, so I'll have a drop across polysilicon, psi p, right? Because at very high gate voltage it will happen. So this psi p, right? This means there will be, but that will not happen near threshold voltage, right? So the polysilicon depletion will not have very large effect on the threshold voltage, because the depletion will only happen when VG is more than VTH, right? When it is depleted, then there will be a drop, right? But that will have an effect on the capacitance, right? So capacitance means, so we are talking about, we have CG, then we have we have COX and CS, right? But again, we have another polysilicon capacitance coming into picture, right? And so this CP will only be there at higher gate voltage, right? So yours 1 by CG, if you are writing, so your 1 by CG will be 1 by COX plus 1 by CS plus 1 by CP, right? And this is a depletion capacitance, right? So as you go on increasing electric field, your CP will reduce, right? So so that will have an effect on the CV characteristic. And what will happen? I'll just show it. No, I'll copy this. I'll copy this one. So that's so your 1 by CG. So in the when you're talking about very high gate voltage, VG greater than VTH, right? 1 by CG will be 1 by COX plus 1 by CS plus 1 by CP. Your CS will not be there because your CS will be very high, so 1 by CS will be 0, but there will be 1 by CP coming into picture, right? So what will happen is at very high gate voltage, you will see that you will have something like this, right? Right. So your COX, because your CP is increasing, right? So you will see your CG will be pulled down, right? And this effect is because this is because of poly depletion effect, right? Poly depletion effect, right? So this is because of silicon poly depletion, and this is typically observed in typically observed in NMOS transistors, right? So you assume that okay, we'll saturate at COX, but it will not saturate at COX. You see there is a gradually fall because at high gate, as you go on increasing the gate voltage, so your CP will increase. Your CP because your CP will change because CP is nothing but your CP will be nothing but epsilon Si by WP, right? Your WP, because your poly depletion effect, your WP will increase, your CP will reduce. If the CP reduces, then it will also interfere in 1 by CG, right? Right? So you'll see a gradually fall, right? So when you see this, you know that okay, the poly depletion effect is coming into picture, right? And this is typical of that. So another thing, right? So if you are given a MOS transistor, let's say you are given a MOS transistor and you are told, okay, find out the oxide thickness, right? Or you are given a MOS capacitor and told, okay, find out the oxide thickness, right? So basically, you take the CV characteristic, and from the CV characteristic, you know that okay, this is COX, this is my COX, the capacitance in inversion or accumulation. And if you know this COX, you measure this COX, then your TOX is nothing but so okay, let me write down. COX is nothing but EOX by TOX. So your TOX will be nothing but EOX by COX, right? So this is how you calculate your oxide thickness, right? But that is not possible to do in a typical MOS transistor in the inversion, because inversion your capacitance is not oxide capacitance, your poly depletion capacitance also comes in the picture. So generally you do it in the accumulation, right? So you just look at the accumulation, and from the accumulation you find the oxide thickness, right? So because see okay, so we'll come to the other things later. So this is how your CV changes because of the poly depletion effect. All right. Any questions here?
Sir, so this effect was not there for lower voltages. This came into picture for higher voltages.
Because poly is very highly doped, it will only deplete when the electric field is very high, right?
So otherwise, up till then, it will behave as a metal and uniformly doped thing. But for very high fields, it will start depleting from lower surface.
Exactly, right? So this will only happen at very high electric field, right? See, imagine you have lot of electron. This is N plus polysilicon, right? So when you have a N plus polysilicon, Or you think of if you have a P sub here and P sub is very highly doped. Depletion is very difficult, right? You need very high electric field to deplete it, right? Right? If your substrate is very highly doped, you need high electric field to deplete, right? Right. Similarly,
Yes, sir.
your N plus polysilicon is your gate and that's very highly doped, right? So you need very high electric field to deplete. That's the reason this poly depletion effect can be observed only when the VG is much higher than your threshold voltage, right? And that is typically we do, right? Because in a typical MOS transistor, your threshold voltage is around 0.4, 0.5 volt, but you operate your transistor at 1.5, 1.6 volt. That means you're going to that field, right? Level.
Okay, so sir, it will be like for 0.4, 0.5 VT, so we can see this effect at 1 volt, 1.5 volt. It will start
Yeah, if
coming
you go
into
to very
picture.
high voltage, that's the reason, right? If you go to high voltage, the field, then because if this is 0.4, 0.5 volt, then you could observe it mostly around 0.7, 0.8 volt on the field somehow increase, right? But then with this field, right, you are seeing this slope, right? With this field, it will start, as your field is increasing, your surface is depleting more and more, and you will see your capacitance reducing, right?
Yes, sir. Yes, sir. So typically it will start from like, if it is for 0.4, so around 1 volt, and after that I will like predominantly see I can see this effect. Yes, sir.
Yeah, you could only see it in very high electric field. Okay. Done. Any questions about CV? Then otherwise we have done with CV characteristics of mass transistor and mass capacitor, right? So capacitance voltage is a very important characteristics. We'll see later, right? Why it is a very important? Why the capacitance is very important, right? Okay, so now I'll go to the IV characteristics, right? So I have some time, so I'll go to IV characteristic. Okay. So when you're talking about IV characteristics, right? So let's start with inversion because um, let's start with inversion. Then we'll come back to the weak inversion or depletion region, right? So when you're talking about IV, right? So once your surface is inverted, right? Your MOS transistor is inverted. Okay, let me go, right? So let's say if you're applying, let's say this is your transistor, so you're applying a gate voltage more than threshold voltage, right? So if you're applying gate voltage more than threshold voltage, so you have depletion charges as well as you have a sheet of electrons sitting at the surface, right? So then if you apply a voltage difference, if you apply a voltage difference between source and drain, let's say I apply a voltage VD here, that means I am applying a voltage difference. So these electrons will move, right? So they'll go from source towards drain because they'll slowly drift, right? If you go on increasing your VD, so electrons will slowly drift because there is an electric field, right? So the electrons will go from source and drain, and you'll get a current from drain to source. Okay, so so that is in inversion. So let's focus on this part. Let's say our surface is inverted, and we are talking about current. So here, your transport, right? Because we discussed about electrostatic. Electrostatic deals with your formation of charge, right? Then your transport means if you apply voltage difference, your electrons will move, and the electrons will move by drift, right? Because there is no diffusion, right? Because there is no concentration gradient. If you see from the source side and drain side, there is no difference in electron concentration, right? So electrons concentration is same, right? So there is no diffusion, right? So that means drift. And we know that drift means they'll move with a velocity, which is nothing but mobility times electric field, right? And electric field, if this direction is y direction, because we had taken this direction as x, so this is the direction of electric field in the y direction, right? So mu times electric field. Okay, so let's derive, right? So before we do the derivation, let me talk about, because we have seen the band diagram in the x direction. We have, because now we are talking about y direction, right? So let's see how the band diagram looks like in the y direction, right? So this is when Vg equal to VFB. So this is your band diagram when gate voltage equal to flat band voltage, right? Your bands are flat, right? Because you do not have any charge in the silicon. So this is a typical band diagram in the y direction, right? So this is your source. In the left hand side you have source, right hand side you have drain, and बीच में तुम्हारा substrate है, right? So you have so this is n type. So this region is n, this region is n, and you have p between, right? And this is something like a NPN BJT का जो BJT जैसा band diagram है. You have. And we are talking about this field which is QVBI. This is a barrier potential which is QVBI, and this VBI is nothing but KT by Q ln NAND by NI square, right? ND is doping of N plus regions, right? Okay, so now if I apply some gate voltage, I have a gate voltage which is somewhere between VFB and VTH, right? Right. So I so I reduce this barrier, right? So if you remember the principle of operation of MOS transistor, right? So if you go on increasing the gate voltage above flat band voltage, so you will have charges, then you will develop a surface potential. You will have some drop in the silicon, right? And that psi s, because of the psi s, your junctions will be far biased, right? So basically, you are pushing. So you could think of, you have your gate is here, right? Your gate is here. If you are applying a voltage and your capacitive effect, so if you are applying a gate voltage, that means your bands are pushed down, right? So your bands are pushed down, that means you are developing a surface potential, right? So so your bands will be pushed down and your barrier will be reduced by this factor, right? So your barrier will be Q VBI minus psi s, right? So this is the band diagram when your VG is somewhere between VFB and VTH, right? And because your barrier has reduced, so you will have electron injection. So electron will be injected from both the sides, right? Because you will have electron injection, right? Because your barrier has reduced, and that reduced by a factor of Q psi s, right? And psi s is a function of VG, right? Okay. Now, if you then after some point you have a lot of electrons, because as you go on increasing Vg, your psi s is increased, your barrier has reduced, then you're injecting more and more electrons to the substrate, and there is an electric field. The electrons are pulled up and they're sitting at the surface, right? Then your psi s will increase, then it will saturate at psi 2 psi b, right? Your psi s, right? Okay. So you have a channel formed, right? So when Vg greater than VTH, and you have a channel formed, right? You have a channel, right? So channel formed, right? So now if I apply a drain voltage, so what will happen? I'll apply drain voltage. So basically I'm giving drain voltage here, right? VD, I am applying a drain voltage. That means my bands in the drain side is pushed down by QVD, right? So energy is Q times VD minus Q times VD. So VD is positive, the energy is negative, so your bands will be pulled down, right? So your EC in the drain side will pull down by QVD, right? But your source side is not changing, right? Source side, your VS is at ground, right? You have something like this, right? Uh, your body is ground, your drain, you are giving a voltage of VD here, but source is at ground, right? This is your VG, right? Right. So when you pull down this QVD, right? So if you look at this band diagram, look at this blue lines, right? So your green to red is just by increasing Vg, By increasing the gate voltage, you have some surface potential and your barriers will be lowered by that surface potential, right? From red to blue, this is because of application of drain voltage, right? When you apply drain voltage, you pull down the drain side that and you are creating a gradient in the channel, right? So if you have an electric field in the y direction, so because of the electric field, there will be a gradient in the AC and EV, right? So you could think of, right? So you could think of also like this. So let's say this is my channel, right? And this side, one side of the channel is connected to ground, right? Your channel is sitting here, right? This is my channel, right? And this side is your VD. I'm applying a drain voltage, right? So your channel is a highly conductive region, right? So if I plot, this direction is Y, right? If I plot in the Y direction, right, voltage from left hand side to right hand side, you will see that your voltage will increase from 0 this side to VD in the other side, right? So you could think of this as a resistor or a conductor, right? Conductor, across the conductor, you are applying a voltage VD. That means your voltage in the conductor will linearly change also from one side to the other side, right? So it will go from 0 to VD. Yeah, right? Right. So this is the Vy, and that's the your band will also bend, right? So that means there is an electric field, and the electric field will be in this direction, right? Electric field is in this direction. You are right, and that's the reason your bands will bend. Means there will be gradient in the conduction band, there will be gradient in the valence band, and that gradient is represents the your electric field. This gradient represents your drift velocity, right? Because if your mobility is constant, your electric field is drift velocity is related. So that gradient tells you what is your velocity, how much how the electrons will move from source side to the drain side. Because you could find this slope, right? And that slope, you could think of, you are putting the electrons at this point here, you are putting electrons at this point, and the electrons are rolling down, right? And that rolling down at a particular velocity, and that velocity is your drift velocity, right? And they are rolling down from source side to the drain side, and they are collected at the drain side, right? And if I talk about how much time, if I'm putting some electrons in the source side, right, how much time does it take to reach drain, right? That time is the transit time. How much time the electrons take to go from source to drain side. This transit time is nothing but if the length is L by VD, right? So this is my drift velocity. Drift velocity is nothing but mobility times electric field. If you go on increasing the electric field, your drift velocity will increase. That means how will you increase EY? EY is nothing but by changing the drain voltage. If you increase the drain voltage, your electric field in the Y direction will change, your drift velocity will also change, and your transit time will also reduce, and your means see. And then you think of, right, if I put a counter here, right, and I count, okay, per second how much electrons I'm receiving here, that will depend on the velocity, right? That's the reason your current will depend on velocity, right? So current is nothing but accumulation of, means your dq by dt, right? Dq by dt is your current, right? And this time is the transit time, right? So your q is the inversion charge, and the t is the transit time, right? And if you want to have very high current, right, your current is dq by dt, right? This is your inversion charge, this is the transit time. If you want very high current, right, very high current, because when you are designing a transistor, we want your current to be very high at a particular voltage, right? So we want to have very high inversion charge, right? Or we have to have very low transit time, right? And so we will discuss these things. So your transit, if you want to reduce transit time, you have to increase the drift velocity. That could be done by changing the drain voltage, right? But drift velocity cannot be increased. If you go on increasing VD, your drift velocity will saturate at some point, right? You cannot just by changing the VD, you cannot just go on increasing your drift velocity. Okay, so this is the band diagram. So at any point, right, your surface potential, the potential drop in the silicon is nothing but your potential drop in the silicon, VSI, if I write. So this was psi s before, but now I have some Vy at any point, right? So if you look at the potential drop, so potential drop will change from source side to the drain side, right? You see the your drop is nothing but Q psi s plus Q. I mean, this is the energy. So if you look at the potential, is psi s plus Vy, right? So your potential drop will be psi s and Vy. If there is no drain voltage, the drop in the silicon is psi s. Vy is 0, right? If your Vd is 0, that means your Vy is 0. So your potential drop, your silicon as Y is constant. This is psi s, right? So there is a constant voltage in the channel. If there is a channel is equipotential surface, if there is no potential gradient, so there will be no current, right? Right? Okay. Okay. Now, if you understood this, understood the band diagram, then if I go to this gate voltage, right? So because I need charge, right? For current, the first thing I need is charge, right? So let's go back to our earlier equation. Your Vg, we could write this because your is flat band voltage plus voltage drop in the oxide plus voltage drop in the silicon. The voltage drop in the silicon will be psi s plus Vy now, right? Right. So then I could also write down this by VFB, and your voltage drop in oxide is nothing but QD by Cox plus Q inversion by Cox. Total silicon charge by divided by Cox plus psi s plus Vy, right? If I'm looking at Vg greater than Vts, because we have started with, because IV characteristic, we started with, let's say your gate voltage is more than 30 volts. Yeah, ohm.
Sir, this Vy was coming due to Vt, so why we are adding it in Vg?
Vy is coming because of Vt.
Vd.
Yeah, because I'm talking about Vd, right? I have a finite Vd, right? Because of Vd, my silicon drop becomes psi s plus Vy, right? So,
Yes,
right?
sir. So,
Yeah, right? Huh.
so sir, but I have already applied a Vg, then I am applying Vd. So that Vy term is due to, that drop is due to Vd. So
No,
now
this
why
is
I'm
pretty good, but if I solve the KVL from one side to other side, what should I do? KVL will be Vg, your gate voltage is your voltage drop in the oxide plus voltage drop in the silicon, right? Right?
Yes, sir.
And voltage drop in the silicon has changed because of Vd applied Vd, right?
Yes, sir.
Right? Because that's what we decide. If you look at this band diagram, so the voltage drop in the silicon has changed. This is Q psi, means energy. This psi s plus Vy becomes the voltage drop in the silicon, right?
Yes, sir.
No, if there are more doubt, let's clarify this point, right? Om, did you get it?
Yes, sir.
Okay. I'm talking about everything. Okay, Sarda, Monica, Om, sorry, Swati, Aditya. So all of you got it?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So now I could write down this by, because when Vg more than Vth, your psi s equal to 2πV, right? Because psi s is fixed at 2π, 2πV, right? So your Vg, you could write it like this. And if you see this part, right? So VFB, this plus 2 psi b, this part, right? This is your threshold voltage. Your threshold voltage is, what is your threshold voltage we have derived? Threshold voltage is flat band voltage plus 2 psi b plus 1 by Cox root over 2 epsilon si Q&A into psi b, right? So this is your threshold voltage, right? So I could write my gate voltage as this in this way, right? So your gate voltage is Q inversion by Cox plus Vth plus Vy, and this Q inversion, right, will be Cox times Vg minus Vth minus Vy, right? Right. So now the inversion charge, right? Inversion charge, because your potential it's changing across the surface, right, from source side to drain side, your inversion charge will also change, right? And inversion charge will be a function of y, and your inversion charge will be, you could write it like Cox minus, right? So this is the inversion charge. Please keep in mind. So the unit here is per centimeter square. This is the charge per centimeter square, right? Right. Your Cox is per centimeter square, farad per centimeter square. Now this is the voltage, right? So this is coulomb, right? Coulomb per centimeter square, right? Your Q inversion. Okay, and this charge, this Q inversion is mobile, right? So because your depletion, there is depletion charge, but that depletion charge will not move, right? But your Q inversion will move, right? And your current is because of this Q inversion, right? And so that's why we have to take, means that's why we will only take this part, right? So your Q inversion is nothing but Cox times Vg minus Vts minus Vy. Okay, now let's say this is my inversion layer, right? So this is my inversion layer, right? And inversion layer has a thickness of T inversion, and width I have W and L, right? So this is my inversion layer. So if I total inversion charge, right? So total inversion charge will be Q, your Q times N, right? Because you have electrons, all are electrons here, right? Q times N, W times L times T inversion. Can I write? So this is the number of electrons, and this is the volume WL into T inversion, right? And the charge is Q, and this will be negative. Let's forget about negative. Let's say this is Q N times WL T inversion, right? So this is the total inversion charge. The unit is coulomb, right? Right. This is the total inversion charge, right? And these inversion charge will move, right? Your depletion charge is not moving. Now, if I want to have inversion charge per unit area, right? If I want to have, because I am more interested in inversion charge per unit area, charge per unit area, right? So this will be Q N W L T inversion. Area is nothing but W times L, right? So I can have this Q N times T inversion, right? So this is my inversion charge per unit area, right? Okay, this is the inversion charge per unit area, and this is, I write this as Q inversion, right? So let's say this is Q inversion. The unit is per coulomb per centimeter square. Coulomb per centimeter square. Okay. So now, if I apply some VD and I want to find current, right? So I have applied some drain voltage, right? So let's say let's say take a small part in that channel, right? So let's say I took a small portion of the inversion charge. Let's say the thickness or the length of this layer or length of this small part is dy, right? And the voltage drop in that small part is dVy, right? So voltage drop is dVy, right? So I have dVy drop across this small part, right? So what does this mean? Electrons, if electrons are coming, so at this surface, they are coming with some drift velocity, or yeah. So drift velocity. Okay, so the velocity of electron is constant, right? So basically, the velocity cannot change at any time. Means velocity cannot be a function of y, right? So if they're moving at a velocity, they're moving at some velocity, means some velocity, right? So here, if I'm talking about drift velocity Vd, right? Mu times electric field in this direction, And electric field in this direction is dV by dy, right? Mu, this dV by dy, right? So, okay. So if the time taken by the electron to pass this distance dy is will be, right? So how much time means basically this will be dy by Vd, right? So time taken by the electron. So let's say this is 0.1 and this is 0.2, right? Time taken by the electron to go from 0.1 to 0.2, right? Between T1 to 2, right? So this is nothing but dy by Vd, right? So I could write down this as dy, Vd is mu dV. Okay, let's look, yeah, dy by dV, Vd, right? So time taken by. So how many charge, if I look at the Q inversion in this region, in this small region, Q inversion per centimeter square. So how much charge I have? So this charge I have is around Qn times T inversion. Okay, so total charge that I have, charge in this small region, right? So total charge in this small region, this yellow or dark yellow part, right? This dark yellow part, right? So I could write down this as number of electrons total Qn, your W, then your dy, right? W times dy times T inversion, right? And so I could also write down this is Q inversion for unit area, right? This Q inversion is just Q and T inversion. Times W dy. Right, this is the total number of charge, right? So total charge, right? Total inversion charge, right? So let's say this is total charge, right? Right. So, and I am moving this total charge from one side to the other side, right? So the current that I'm talking about, so this will be Q inversion W dy by time. Let's say it takes time, right? And time is nothing but Q inversion W dy. So they will move dy, means because the time taken to for the electrons to transit dy distance is dy times Vd. So this is nothing but Q inversion W times Vd, right? Right. So this Q inversion, this is the per unit area. I know, right? So this is nothing but I could write down. This is VGS minus BTH minus Vy, right? Uh, times W, Vd is mu dV by dy, right? So, and this is the current, right? So, this will be the current. So I could also write down this as ID times dy is mu W Cox Vgs minus Vth minus dy dV, right? So this is the current I am getting from this dy, right? So when the charge when the electrons move from one side of the dy to the other side, right? The electrons, so this is the current I'm getting if I move from one side of this dy to the other side. So if I want to find the total current, because I'll have such large number of such small region, so if I could integrate it from 0 to L, because this length is L, so I could integrate from 0 to L, and this dV I could integrate from 0 to VDS, right? So then if I do that, let me right? So this will be ID times L equal to mu W Cox VGS minus VTH times V minus half V square 0 to VDS. Sorry, 0 to VDS, and this is nothing but mu W Cox VGS minus VTH times VDS minus half VTS square, right? And your ID is nothing but mu Cox W by L VGS minus VTH half VTS square, right? Right. So this is how this is a very simple form of equation. I mean, simple form of current that you have derived. So your VGS will be your ID, your current will be mu Cox W by L times VGS minus VTS into VDS minus R VTS square. And you all of you know this current. So right. So know this equation, right? This is a very standard current equation for the MOS transistor, right? Okay, maybe I'll stop here because we have already 12:54. I'll not take more time. I'll stop here, but we could have some time for discussion.